Let's see here. Or if, yeah. Gosh, go away, buttons that don't need you to be there. Just want to show you all one thing before I start talking about math. So when you look in Canvas at our co-class, not that I expect you to be looking there often, but if everyone could please sometime before the end of the quarter, fill out this evaluation that I'm about to make available. It probably takes like 5 minutes. You might have done it before for a co-class. It's anonymous. Your feedback is appreciated. My boss would certainly love for you to do it. So please do it when you have a minute. I'll remind you probably again. That's all. All right. So last 2 weeks of class, got some probability and principles of counting and all that kind of good stuff. If you've ever taken a stats class, some of this might seem familiar-ish to you, some of it might not. If you haven't, that's also fine. I need paper. Where's my paper? All over the place here. I'll say a few words before we get going. One generally good rule of thumb, which you have to be a little bit careful about applying, but if you're careful about how you say things, you'll be okay. And actually that brings up another point is reading things carefully, as always, is important. But I'd say that one good rule of thumb is that when you're talking about events happening and their probability or how many ways it can happen, typically when you say one thing and another thing happens, that often means we multiply things together in some way, shape, or form. Whereas if you say one thing happens or another thing happens, that often translates into adding things together. So that's just something to keep in mind as we move forward. And I will definitely circle back to that idea often. If I could find my notes. Okay, sure. So let's talk about some principles of counting, which sounds very basic. Like counting, sure, counting like where you kind of start with math, but it can be more complicated than it sounds, like much of mathematics. Welcome to March. 12.1, the principles of counting. Let's look at an example. He did one like this in class, or he did something similar last Friday where he talked about, I don't remember what the example was exactly. I was just watching it. It was like 4 or something and 2 or something. It was rolling a die and flipping a coin. How many outcomes were there? Let's look at a slightly different example. So let's say we're planning a class schedule. And there are 3 stats classes to choose from. Let's say stats 13 classes to choose from. We won't worry about like different discussion times. We'll just say that there's 3 different stats classes to choose from, right? Section 1, 2, or 3, or A, B, or C, right? We're not getting too complicated here. There are 2 Biosci 1A sections to choose from. And there are 4 chemistry 2C sections to choose from. Sounds like a terrible schedule. Assuming none of the classes overlap, how many different possible schedules could we make? Relatively visible. All right, so yes, so we're planning a class schedule, and there are 3 stats 13 classes to choose from, or 3 sections of stats 13. Sorry. 2 biosci 1A sections and 4 chem 2C sections. How many different possible schedules can we make up? Again, assuming no overlap. Well, let's think about this way. So let's pick a stats section first. Let's say we pick the first section of stats. For that section of stats we picked, then we have 2 possible biosci sections, either the first one or the second one. And for each of those biosci sections, we have 4 possible chem sections. So for this one section of stats, there's, let's see, 1, 2, 3, 4, 5, 6, 7, 8 different schedules we could have made using either biosci section and either of the 4 chemistry sections. But that's not the only section of stats, right? We could repeat this diagram for the second section of stats. I don't actually want to draw it all out because it's just literally drawing the same picture, right? You'd have this going to biosci first section, second section, and then each of these would have 4 coming off of them. And the same thing for the third section of statistics. You'd have 2 biosci sections, and then each of those would have 4 different chemistry sections. If we count up all the different schedules, right? So check this out. You should watch this for a second. We can either do like the first section of stats, the first section of biosci, the first section of chemistry, or the first section of stats, the first section of biosci, the second section of chemistry, or this path. Basically, every path that ends at one of these sections of chemistry is a different possible schedule. Because every path is going to have something different than any other path. So how many different terminal places are there? Well, it looks like there's 4, 8, 12, 16, 20, 24 possibilities. 24 possible schedules, which we could have calculated by multiplying the number of sections of stats. So the number of stat sections times the number of biosci sections times the number of chemistry sections, which would have been 3 times 2 times 4, which is 24. And that's kind of the basic idea, is that if you have some number of independent events and each independent event has some number of choices, you just multiply all those choices by each other to get the total number of possibilities. I know he kind of wrote a formula for this. I don't think you really even need a formula, to be honest. It's just kind of like, yeah, you have this many options for part A, this many options for part B, this many options for part C, multiply those options together, and that's how many total possible ways of doing it there are. Looking at another example, just to kind of drive the point home. We'll try to write not too many words here, or we'll try to write them nicely. Example 1. Example 2 here. In a study of the effects of light and fertilizer on plant growth, we plan to study 5 different fertilizers and 3 different light levels. Now, it would be bad science to just have one plant for each possible combination, right? Maybe that plant's just not a great plant. So we're also going to, do our due diligence here. We don't have unlimited funds, so we're going to spend our money wisely. We're going to have 4 replicates, meaning 4 plants for each possible combination of light and fertilizer. How many plants do we need to buy? Well, it's not too hard to do the math there. There's 5 different levels of fertilizer. There's 3 different light levels. That's 5 times 3, which is 15 different possible combinations of light and fertilizer. And then we're going to buy 4 plants for each possible combination. So we're going to have 60 plants altogether. You could draw a picture. I don't think we need to draw a picture, but I'll point out, like, if you kind of arrange the plants into a grid so that all the plants in the first column have light level, let's say I call it A, second column have light level B, and the third column have light level C. And then in row 1, we have the first fertilizer, row 2, we have the second fertilizer, etc. We can see, oh yeah, each of these little circles here represents a different combination of light and fertilizer. And then in each of those little circles with that light and fertilizer combination, we're going to put 4 plants. 4 plants here, 4 plants here, 4 plants here, et cetera, et cetera, et cetera. So we're going to have 15 circles, each with 4 plants. Oh yeah, that's going to be 5 times 3 times 4 equals 60 plants total. It seems pretty straightforward. It is pretty straightforward, but do make sure you've thought about it a little bit, right? That you're just taking the number of ways of getting one thing times the number of ways of getting another thing, and so on, and so on, and so on. I think I have one more example in mind before we go on. Sure. Another kind of typical example people often talk about is license plates. So often, at least license plates that I notice currently usually are one number, then 3 letters, then another 3 numbers. Assuming that's what we have as far as the order of characters on a license plate, how many possible license plate combinations are there? Well, how many numbers can we start with? Or how many different numbers are there to start with? Is it 9 or 10? That's a good question. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Again, not making any assumptions about what you're allowed to start with or not allowed to start with, because there typically are some restrictions or words you're not allowed to spell, but we're going to pretend like none of those restrictions exist and say, yeah, for the first spot, there's 10 choices. You can put any of the 10 letters in the first, or any of the 10 digits in the first spot. And then for the next 3 spots, how many choices are there? Well, how many letters in the alphabet are there? How many letters in the alphabet are there? 26. A useful fact, and it will come up because we also talk about decks of playing cards, is a deck of playing cards has 52 cards, which is twice the number of letters in the alphabet. Which is useful because sometimes it's important to think about the fact that each suit in a deck of playing cards has 13 ranks. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. So there's 13 clubs, there's 13 diamonds, there's 13 hearts, there's 13 spades in the deck of cards. There's 26 black cards, the number of letters in an alphabet. There's 26 red cards. So something that I think is useful. Who knows if it really is. So there's 26 choices for each of the letters, because we're allowed to repeat if we want. And then for the last 3 digits, there's again 10 choices for each digit. So the number of possible license plates is 10 times 10 times 10 times 10, or 10 to the 4th times 26 and 26 and 26, which is 26 to the 3rd. And I wouldn't do any more work than that. There's no reason to simplify that number. All right. Oh, not even. So we're just counting numbers of things. That's kind of the idea, but that's not all we're going to do. We're also going to talk about permutations. So when you hear the word permutation, you should think of kind of how many different ways can you reorder something is often a way I like to think of it. Or the number of arrangements, and specifically here, the order of things matters. All right, so let's look at some examples. At the library. Ooh, exciting. Right? I'm numbering things, I'm trying to number things, not very well. Sure. Example number 3, even though we technically did 3. Sure, at the library. The library, we notice on the shelf that there are 4 different math books. There are 5 different chemistry books. And 6 different biology books. The first question is, how many ways can we arrange the books on the shelf? Usually when we talk about like how many ways can you place things in a row or in a space or next to each other in some way, we often like to kind of draw it out, meaning we make a bunch of blank spaces representing kind of what can go in each slot. So we're thinking about 15 books, right? There's a total of 15 books all being next to each other. And they're going to be, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we usually talk about how many choices we have. So I haven't determined anything yet. If I'm going to put any of these books to put in the leftmost spot, how many choices are there for that book? Well, there's 15 books, there's 15 choices, right? Every book is different, so any different choice matters. So there's 15 possible choices for that first book. And now we move over to the next spot. We said, well, we picked the book to be in the first spot. I don't know which book I picked. Let's pretend it was one of the math books. And now in the next spot, since I've chosen one of the books to already put down, now there's only 14 choices left for the next spot. But we are going to multiply them together because there's 15 choices where I can pick any of the 15 books for the first spot and then any of the 14 remaining for the second spot. So there's going to be whatever that number is, 150 times. There's 210 choices already just for the book that goes in the first spot and the book that goes in the second spot. And then there's 13 choices for the next one, and 12, and 11, and 10, all the way down to 3 times 2 times. There's no choices. So it's funny, we like at the very end, there aren't any choices left because there's only one book, but we still would say that we're going to multiply by 1. You're not going to multiply by 0. Nobody wants to write this all out, right? I don't want to write the number of choices are 15 times 14 times 13 times 12, right? The number of possible arrangements or the number of ways is 15 times 14 times 13 times 12, all the way down to 3 times 2 times 1, which we're going to write as 15 factorial. If you haven't seen that notation before, it's just an exclamation point, and it literally just means whatever number you've written, multiply it by every integer that is smaller until you get down to 1. Couple notes about this. Note. So for example, 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, which is 2. 1 factorial is kind of unexciting. It's 1. And something that probably isn't super important, but I'm just going to say it because it might come up. 0 factorial is defined to be equal to 1, which might seem kind of weird. We will talk about why we need it to be true a little bit later. It's similar to the reason that like something raised to the 0th power is equal to 1. Because there are rules that make it so it needs to be. Really is the reason. But we'll come back around to that, I promise. Follow-up question, part B. How many ways can we arrange the books if books from the same subject have to be next to each other? Have to be adjacent. There's less words to write the same sentence. All right, well, let's just pick one subject. Let's say math is first, because math is the best. So for the math textbooks that all have to be next to each other, let's see, there's 4 different math books. For the 4 math books, how many different ways are there of arranging them? Well, there's 4 choices for the first math book, 3 for the second, 2 for the third, and 1 for the fourth. So there's 4 factorial choices. For the, I don't care what's next, let's say biology's next. For the biology, well, there are 6 biology books, there's 6 factorial choices, or ways of arranging them. Or I should say really permutations. There's 6 factorial permutations of the 6 biology books, which is kind of a lot. 6 factorial is like 720. There's 720 different ways you could arrange just 6 books. Seems kind of surprising that there's that many ways, to be honest, but there are. And then for the chemistry, there's 5 factorial ways. But we've made an assumption that doesn't have to be true. I assumed math was first, biology was second, and chemistry was third, from left to right. But we could have put biology first and math second and chemistry third, or chem first and biology then math, or how many different ways are there of ordering the different subjects? Not quite. A little too many. How many subjects are there? It's not 3 different ways, 3 factorial ways. There's 3 different ways. So there's 3 choices for the subject that goes first, math, chem, or biology. And then after that, there's 2 choices for what's next. And then there's whatever's left for the last spot. So there's all these ways times 3 factorial ways of permuting which subject is first. Just to really show you, because 6 is long enough, we can do that. I'll point out that you can either do math, bio, chem, math, chem, bio, biochem, math, bio, math, chem, or chem, bio, math, or chem, math, bio. So there really are 6 ways you can organize just the subjects. And then within each organization, the number of ways you can order the books. So our end result here is that the total is 6 factorial times 5 factorial times 4 factorial times 3 factorial. This factorial notation is going to get a lot of use in these next couple weeks, so get comfortable with it. It's going to be frequent, and you usually don't want to simplify. Like usually you just want to leave a factorial as a factorial because for 2 reasons. One, well, I'd say if someone was grading your homework, it'd be easier for them to know what you meant if you wrote 6 factorial versus writing 720. Like if you just gave the whole answer as 720 times 120 times 24 times 6 and then actually got a number from that, that's not meaningful really. I don't know you knew what you were doing if I see that answer. I want to see this answer because I'm like, oh, they clearly knew what they were doing. They knew that they should do the biology books, the chem books, and the math books, and then multiply by the number of ways you can order those 3 subjects. So it's kind of almost better to leave your answers in an unsimplified form here. So write something down. The number of arrangements, also known as permutations, of n objects is equal to n factorial. And again, I'll just note n factorial is just n multiplied by the next smallest integer, multiplied by the next smallest integer, multiplied by the next smallest integer, all the way down to the smallest positive integer, which is 1. Something doesn't want to say it. I know what it was. No, actually, I don't think I can say that. That's not true. All right, so then we just like to start asking kind of questions that feel, I will be honest, a little bit kind of contrived. Ooh, what did I just do? I did something. Like, we're just like, here's something that seems like we'll do because It doesn't feel like it's got a lot of value to it, but we're building up our knowledge so that we can do other stuff later. So here's a question. How many different ways to permute the letters in the word math? Now, I want to point something out. Someone might ask this question in the following way. They might say, how many different words can we make from the letters in the word math? And if you were thinking about actual real words, it's probably one. There might be another word in there that has all four letters. I don't think vam is a word though, but whatever. That's not the point. The point is that when we say something is a word, when we're talking about permutations, we just mean a different arrangement of the four letters. I don't care if it actually spells a real word or not. So in this case, well, there's going to be, I think, 4 factorial options. There's 4 choices for the first letter, 3 choices for the second letter, 2 for the third, 1 for the fourth. We could write them all out. I don't think we should. We could write out 24 things, but let's actually write 6 of them. So I'll just point out, if we write 6 of them, let's say we start with, I'm going to start with letter A. So then we can have A, then M, then T, then H, or A, then M, then H, then T. I will point out there is kind of a method to the way I try to write out these permutations if I'm trying. Usually you shouldn't do this, but if you're being asked to write them out, which occasionally you might be, there is a method I like to use. I'm keeping the stuff further left constant as long as possible. So I'm leaving the A as is, I'm leaving the M as is, the T and the H are changing first because they're the furthest to the right. So the first thing I do is, well, I'm going to keep A and M constant, T and H can switch places, but then there's nothing else to do here. I can't get another combination with A and M still there. I should say permutation. So now the M gets to move over. I'm going to move the M to one of these spots. Actually, I'm going to move the T or the H over, really. So I'm going to put the H here, and then I'm going to have the M and the T. Then the H and the A are going to hang out, and I'm going to switch the M and the T to T and M. And then I've exhausted the ways we can have A then H. So then I'm going to have, I've done A then M, I've done A then H. Now I'm going to do A then T. And then I'm going to have M and H, and then I'm going to have H and M. So we can see for just starting with A, there's 1, 2, 3, 4, 5, 6 possibilities. And then similarly, starting with M, there'd be 6 more possibilities. Starting with T, there'd be 6 more possibilities. Starting with H, there'd be 6 more possibilities. 6 plus 6 plus 6 plus 6, it's 4 times 6, which is 24. So again, just seeing that, oh yeah, there really are 24 different ways of arranging these 4 letters. Now here's where things get interesting. Same question, but what if the word was data? Well, the problem here is that we're not going to have as many combinations or permutations because that A and that A don't look any different. So normally, in fact, let's do something here. Let's pretend like we're going to pretend for a moment the A's are distinguishable from one another, are distinguishable. So let's say we've got the word data and we have A1 and A2. Well, then there's definitely going to be 24 ways of arranging these 4 different looking things. So there's going to be 4 factorial equal to 24 total possibilities. But then we're going to have some overcounting because really this combination here and this combination here where the A2 and the A1 have switched places shouldn't both be counted as different because they're not really different. So what we actually have to do here is take our 24 combinations or permutations and divide by the number of ways you can interchange the A's with each other, which in this case is just 2 or 2 factorial. There's actually 12 different ways of arranging these 4 letters. to get unique words. Words in quotes. So the idea here is basically you take the number of permutations and then you divide by the number of ways you can permute the things that are the same as each other. Even though I don't really want to, I do think it's worth writing these ones out. It's kind of terrible, but I think we're going to do it just so you can really see, because I can see the looks on your faces. You don't really look like you really believe me just yet. So let's write them all out. You don't have to write them all. I'm going to write them all out, and I'm going to do it fast. So let's see here. So I'm going to follow my process. So let's start. I do have to write the A1s and the A2s, which is kind of annoying. So let's start with D, T, A1, A2, and then D, T, A2, A1. Then we'll put the A1 second, D, A1, A2, T, D, A1, T, A2. And then we're going to have D, A2 next, T, A1, and then D, A2, A1, T. And then we'll move over to having T first. T, D, A1, A2, T, D, A2, A1, T, A2, D, A1, T, A2, A1, D, T, and then we have A1 next, D, A2, T, A1, A2, D. We're almost there. We're going to have A1 first now. A1, D, A2, T, A1, D, T, A2, A1, T, A2, D, A1, T, D, A2, A1, A2, D, T, A1, A2, T, D. And then we will go with A2 first. So we have A2, D, A1, T, A2, D, T, A1, A2, T, A1, D, A2, T, D, A1, A2, A1, D, T, and finally A2, A1, T, D. There's all 24 of them. But look, if we ignore the 1s and 2s I just wrote, then we've double counted everything, right? We have DTAA twice. We have DAAT and DAAT twice. We have DATA and DATA twice. We have tada twice. We have tada twice. We have tad twice. We have AA. We have, and then all these are each other. We have ADAT, we have ADTA, we have ATAD, we have ATDA, we have AADT, we have AATD. Everything got counted twice as often as it should. So really, I shouldn't have 24 possibilities or permutations. I should have 12 permutations. So yes, 12 unique permutations of the letters in data. Question, yeah. Well, so the question was how many different ways to arrange the letters in the word data. So without any other information given, we should assume that the first A and the second A, right, they don't look any different than each other. We're not like writing one in cursive and one pen, right? They're totally the same letter. So really, when I'm writing these two things, those are indistinguishable. Both of these are DTAA and DTAA. I shouldn't be counting the same permutation twice. Right, unless it said that. But if it didn't say that, we would assume they were not. So another kind of good question. So let's do two more. So how many ways, or how many ways can we permute the letters in Mississippi? How many letters are there? Let's see. There's 4 S's, there's 4 I's, there's 2 P's, and there's 1 M. So there's 11 letters. So it's going to be 11 factorial. And then we have to divide by the number of ways you could reorder the i's. There's 4 i's. The number of ways you could reorder the s's. There's also 4 s's. And the number of ways you could reorder the p's or interchange the p's, and there's 2 p's. You could also even throw in a 1 factorial down there if you wanted to for the number of ways you could rearrange the m's with themselves. It's just only one of them. In fact, all of our previous answers could have been divided by a 1 factorial for every letter that was a singleton. Because 1 factorial is just 1, it doesn't change anything. So this is the number of ways you could reorder the letters in Mississippi. Or I should say the number of unique ways we could permute the letters in Mississippi. All 11 of them. It's kind of neat. It's kind of not important at all. Okay. One more question, which we're going to come back to. I forgot the numbers. Sorry, the numbers went away. Outside. In a foot race of 10 people, how many different possible ways can there be a first, second, and third place? Well, here's how I would do this. So first, second, and third, well, how many choices are there for first place? Yeah, so it always feels kind of weird to ask this question this way, I think, because you're like, well, James, there's only going to be one first place, whoever's in first. But we don't know who's in first yet. So we're just saying, well, of the 10 people that are out there, any 10 of them could end up being in first place. So not knowing how the race is gone, at the outset, there's 10 different possible people that could be first. And then after someone is first, there's 9 people left to be second, potentially. And after that, there's 3 people left to be third. We don't care about the other 7 places though. So it doesn't matter what the other, like if you wanted to order all 10 of them, you get a very different answer. There'd be a lot more ways of ordering all 10 versus ordering just the first 3. 10 times 9 times 8 is going to be 720 possible ways to award medals. Another way to think about this, so this 10 times 9 times 8 is equal to 10 factorial, the number of ways of ordering or permuting all 10 of the racers, divided by the permutations we don't care about. We don't care how the last 7 people get ordered. So we're going to divide by 7 factorial, which ends up being exactly the same, right? Check it out. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. Or in other words, 10 factorial is 10 times 9 times 8 times 7 factorial divided by 7 factorial. Those cancel and you're left with just 10 times 9 times 8. This is a formula that I'm not in love with personally, but it's fine. Oh yeah, I'm sorry, I forgot one thing. Sorry, this is 10 factorial over 10 minus 3 factorial. And the formula, which again, not a great formula, but it's fine. So here it is anyway, even though you can tell I have disdain for it. The number of permutations of k objects chosen from a group of n objects is written in many different ways. One way of writing it is P of n comma k, or in a calculator, you might see it as n lowercase uppercase p lowercase k. It's equal to n factorial over n minus k. I will point out many calculators have a button for this. If you want to ask about it, I'm happy to show you. Yeah. Enough time. Yeah. So, in contrast to permutations, are combination, which is why I was trying to kind of avoid using that word, even though it's hard for me to avoid. So when someone says a combination versus a permutation, very broadly, permutation, we care what order things are in. It matters. Different order means means we count it as a different result. Whereas combination order does not matter. We don't care about the order of things. We just care about a grouping of so many of these versus like inclusion in a group versus exclusion in a group is kind of the difference between combinations and permutations. So let's look at this example. So for combinations, we typically think the order doesn't matter. For example, how many oh yeah, well we'll start with permutations here. So for the first example, how many permutations of three letters chosen from A, B, C, D, and E are there? Well, we just came up with a formula. Although honestly, when someone asks this question, I really, really don't think about formula. I think, okay, I have three slots, right? I'm trying to permute three letters chosen from A, B, C, and D. Let me ask everybody, how many choices are there for my first letter? If I'm choosing from these letters over here, five. How many for my next letter? And then, right, 5 times 4 times 3, which is 60, which sure you could have written as 5 factorial over 5 minus 2. Sorry, 5 minus 2. Is that right? No, 5 minus 3. I always get the formula backwards. That's why I'm bad at it. That's why I don't like it, probably. Over 5 minus 3 factorial, which is just 5 factorial over 2 factorial, which is 5 times 4 times 3. So great. There's 60 ways or 60 permutations of three letters chosen from these five. And there's a lot, right? You could like first you could pick the first three letters, so like it's like ABC or ACB or A or BAC. You don't need to write this down. BCA, CAB, CBA. So for that choice of three letters, I get these six combinations. But then I can choose A, B, and D, or A, B, and E, or A, C, and D, or A, C, and E, or let me make sure I'm not missing anything. A, D, and E. What am I forgetting here? I'm forgetting I don't have to have A. You could have B, C, and D, or B, C, and E, or B, D, and E, or C, D, and E. 2, 4, 6, 8, 10. Yeah. And for each of those three letters, there's 6 ways of permuting them. And 6 times 10 is 60. So we see, oh yeah, there's definitely 60 permutations. Looking at this, before we even go to the next part, how many different ways are there of just picking any three old letters? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 ways of picking any three letters. So the next question, 7b, how many combinations of three letters from A, B, C, D, and E? The order doesn't matter. We don't care, or not even we don't care. We don't want to overcount each combination by a factor of 6. I don't want to say there's 60 combinations. There's 10. I want to write an exclamation point afterwards to emphasize it, but that would be bad because 10 factorial is everything. There's 10. There's ABC, ABD, ABE, ACD, ACE, ADE. You don't need to write these again. BCD, BCE, BDE, and finally CDE. Here's how you could have calculated that without like writing as much. We could say, well, take the number of permutations, which was 60, and divide by the number of ways of permuting the three things you've chosen. 3 factorial is 6. So this number here, the number of combinations, is equal to the number of permutations, your 5 factorial divided by your 5 minus 3 factorial, and then divided by 3 factorial, the number of ways of arranging or permuting the three things you picked. Now, there's a better way of writing this. It's 5 factorial over 3 factorial times 5 minus 3 factorial. And in this case, that ends up being, well, so here's when you do this kind of, if you actually have to like simplify this, I wouldn't simplify this usually, but if you want to simplify this, there's a lot of canceling you should do first. All right, 5 factorial, 5 times 4 times 3 times 2 times 1, 3 factorial, 3 times 2 times 1, 5 minus 3 is 2 factorial, which is 2 times 1. You don't even need to write the times ones. But look, the 3s, the 2s, and the 1s cancel. You're left with 20 over 2, which is 10. The notation for this, which I do like, well, there's one notation I like. Some people write it as C of n comma k. Some people write it as NCK or NCR. But the best notation, the most mathematical notation, the one I prefer, is this notation. N choose K. It looks like a big parentheses with n on top of k on the bottom. There is no fraction line. It's not a fraction. It's just n over k in tall parentheses. This is called the choose function. Called the choose function. And it's equal to, sorry, let me just use another page here instead of trying to like squeeze it in here. So to reiterate, the number of combinations, not permutations. But actually, I just want to say the words here real quick first. The number of commutations is just number of combinations of some k number of objects out of n objects. It's just the number of permutations divided by the number of ways of permuting the k things you have picked. So it's the, let me write them. The number of combinations of k objects chosen from n objects is read as n choose k, and it is given by n choose k equal to n factorial over k factorial times n minus k factorial. Or in other words, the number of permutations divided by the number of ways of permuting the k things you've chosen. But this is the formula you should probably remember. The thing I like about this formula is the two numbers in the bottom before you factorialize them add up to the thing on the top. Right over here, when I did this formula here, I had 5 factorial over 3 factorial times 2 factorial. Oh yeah, 3 plus 2 adds up to 5. I know I'm not actually getting 5 in the bottom, but I'm just noting that that always happens. So I know it's 201, but let me do one more example. If I wanted to find out how many, oh, where'd that question go? I never phrase it right. I don't want to screw it up. Sure. How many ways are there to form a committee of 3 people from a group of 10? Well, unlike the example where we're trying to put first, second, and third for like people running, now we just want to pick a group of 3. We don't care what order they came in. So in this case, that's going to be 10 choose 3, which is equal to 10 factorial over 3 factorial times 10 minus 3, which is 7 factorial. And then we can simplify this, right? That's going to be, so check out the simplification here. I'm not going to write 10 times 9 times 8 times all the way down. I know that the 10 factorial over 7 factorial is going to give me the 10 times 9 times 8, and the 3 factorial is going to be 3 times 2 times 1. I don't want to write the 7, 6, 5, 4, 3, 2, 1 on the top and the bottom, although I could. I don't think I need to. although I clearly am. But then those cancel, and you're left with 720 divided by 6, which is 120. All right, it's 2:02. I should stop. I have office hours. I'll see y'all later. So yes, in case you hadn't noticed, we're definitely switching directions, right? Very different from everything we've been doing up until now. Yeah, one sec. Thank you. You're welcome.